All right, and like I mentioned, we're going to do section 44 and 45 together in one point. If you look at the sections, they're pretty related. Essentially, the idea I think for section 44 is like they talk about perceptron, which is going to lead into deep neural networks. So since they're so related to each other, and basically it's hard to talk about neural networks without talking about deep learning in general, we're just going to combine them together into one study group, which makes a lot more sense. What was I going to say now? Oh, also, we're skipping over section 42 and 43, right? So we're going right into neural networks, and then this will lead us into tuning, which will be next time on Thursday, and then we'll do into convolutional neural networks, kind of a special application of neural networks, particularly for image recognition, and then into transfer learning, where essentially we have someone else train, or maybe yourself, train with a neural network, and then use those parameters essentially to speed up our own training and stuff like that, which will be really useful. Okay, so I'm going to share my screen, and I'll show you guys also where to find the new notebook. It's on the repo right now. Oops. Sorry, I have to readjust my windows. Okay, so if you go into the repo that we've been using, I'm trying to make some improvements. Note that I kind of put together, like, a little bit easier for us to see module 6 and stuff. We'll eventually get to graph theory and then 43, put under construction because I'm always modifying everything. But we're going to focus on 44 and 45, which will be these 3 sections. Okay, it's labeled right now under deep learning. I think I'm just going to keep it that way, and then neural networks. So we're going to talk about this between today and Thursday. Okay, cool. So, all right, let's go right into it. And we are going to do a first introduction to neural networks. All right, so if we load, there we go. Okay, so kind of quick thing like a neural network is that basically it's another machine learning algorithm. Right now, it's kind of like, to be quite honest, it's a really hot thing in data science and machine learning, is that basically it has a lot of power to it. It's not always like the best algorithm for the job. I say that, making sure you understand like there's a bunch of other algorithms that we can use first before, like you shouldn't, like if you get like a data science problem, like you're making predictions, you probably don't want to just jump in and start using a neural network. One I am particularly fond of, I've mentioned this a few times, is random forest. Random forest is a pretty explainable one. You can understand it, with feature importance pretty quickly. It does reliably well. Usually does a pretty decent job without overfitting too much. And it's pretty quick. You don't have to worry about having it run over a long period of time. Usually it's pretty manageable. There's some disadvantages, for example, like the fact that the model itself will be larger. But for at least an initial part, like you're just trying to get some predictions out, random forest is usually a good first start. So neural networks shouldn't be your first one, but they can be really useful when you have something that's a really complex problem. So neural networks in general, kind of going off a little bit, is that, how do I say this, is that they can actually find really complex patterns in complex data, which should hopefully give you an idea of like when you should use a neural network or when you should think about using a neural network. If it's simple data, in general, you probably don't have to use a neural network. You can use a neural network, you just probably are using using a more powerful tool than you probably need, right? But what the big thing about this is that neural networks aren't actually like new in that sense. They've actually been developed since the 1950s, something called a perceptron network. And the reason why they are doing so well today, 2000, almost 2020, right, is that basically we have 2 things that have really helped us be able to use neural networks to its full potential. One is a lot of data. We're creating data all the time, millions of data points. Neural networks love data. They just eat that up. So the more data you have in general, the better neural networks can find those more complex patterns. And number 2 is computational power. In particular, parallel processing power, like GPUs, and now even more recently, TPUs. GPUs, if you guys remember CPU back from when we talked about big data, right? Computational processing unit. A GPU is a graphical processing unit. And it turns out GPUs actually do a really good job in making parallel processing, which can be optimized or can be used in the training neural networks. The algorithm actually loves using that parallel processing, so we can actually speed it up quite significantly compared to what you'd have to do back, in the 90s and stuff like that. And then TPUs, has anyone heard of a TPU before by chance? Has anyone heard of a GPU before? Like, I don't know if anyone's like, okay, I see some nods. Okay, maybe not. If you're into games in particular, you probably have to buy a discrete graphics card, a GPU. But a TPU is a tensor processing unit. And the idea there is that they're optimized for tensors, certain operations that are meant to do stuff for like artificial neural networks or other machine learning processes. So TPUs are actually relatively new, and those can actually perform even better on trying to train these objects. Okay. So now that we kind of got a little background saying like what neural networks are a little bit in the sense like how they're used, it's good to talk about like the first part, which is basically the perceptron. So real quick, here's just a quick diagram. I believe the curriculum also shows this diagram here. It's a pretty famous one. Essentially, is that the idea for a perceptron is that we're going to feed in 3 different numbers or multiple. It doesn't have to be 3. It could be 2. Could be just 1, I guess. But in general, we're feeding some numbers into this perceptron. It's going to basically, how do I say this? It's going to basically do math in short and basically get this number right in this node. And then in this number, it's going to output some other number. Okay, that's kind of like what a perceptron does. It basically gives in a bunch of data, some numbers, and it's going to output a single number. In general, when we talk about perceptron, what we really mean is that we have some number here like x1, x2, x3, those are all numbers, and they're being multiplied by what we call weights, usually labeled as like W1, W2, and W3. Okay, and then what we do, we basically add them up all together, and that right there is what goes in here. Okay, so basically we're multiplying it by our weights, add them together, sum them together, and you get a number. Okay, so if you imagine this is like the number 1, number 2, number 3, right? Multiplied by like, I don't know, 0.5. Let's say this is like 1, and this is like, I don't know, 1.5, right? That means like, okay, 1 times 0.5, 0.5, plus 2 times 1 is 2, plus 3 times 1.5 is 4.5. So this overall value would be 7. Okay, that's kind of the idea of like what a perceptron does. There's also a little step right here, usually what we'll talk about as an activation function. Basically, there is some kind of usually some nonlinear adjustment to this number, which usually tends to be a number between 0 and 1. Neural networks love to work with numbers between 0 and 1. So that's usually what happens right here. And that final output, let's say, for example, if the number is greater than 6, it just outputs a 1. This output would just be 1. Okay. So that's kind of like how the perceptron works. The parts that you change are basically this x1, x2, and x3. But the weights would be the same, basically, this whatever this kind of decision function right here, this activation function we sometimes call it. Those are the things that would remain constant essentially in the perceptron. And then we would just feed it new numbers and get new outputs. Okay, does that make sense to everyone? Any questions at all? How this overall works? Okay, so this will actually be our building block. Oh, question?
Yeah, how did you get 1?
Oh yeah, so I think in this case, let me kind of go back a little bit. I just erased it. That's okay, I can do it real quick. 0.5 is here. I think I put 1 here and I put 1.5 here as the different weights. Whatever number I put in here, it basically will be this number times 0.5 plus this number times 1 plus this number times 1.5. And then I have some activation here that says, if it's greater than 6, output the number 1. If I'm just making something up. If less than 6, output the number 0. Does that make sense?
Yeah.
Okay, cool. So yeah, if I put in another set of numbers, for example, let's say I put like 0 and I put 2 and 4 here. That would be 2 times 0.05, so 1 plus 0 plus 4, 2, 6. This would be 7. That would also output 1. Okay, so that's kind of how we're going on. All right, so this might help a little bit to see like what this looks like in code a little bit. So we have a little scenario here. Don't worry about this function right here. This is basically just for us to kind of play around with a little bit. But what we're going to basically do is we're going to take in 3 numbers. Basically think of like x1, x2, and then we actually call like this x3, we're going to call this b as the bias. In general, we kind of have this extra bias term. And what we're going to do here is say, okay, we combine these together. And what we want to do is basically have this output act like a certain thing. We want certain outputs for certain inputs. And so if anyone's familiar with like logic gates, has anyone heard that before? Logic gates. So this is more computer science-y kind of thing. This is a classic example. But a logic gate basically is like, all right, if you have A and B, what is C? And so you can think of like, you know, in Python, we can think of, or just computer science, is 1 is true, 0 is false. And we have something called a truth table. So for example, if we have A is 1, which is true, and B is 1, or true and true, A and B should also give us true. If we had something like 1 and 0, right, true and false, the overall logic would be saying C should be 0. Does that make sense to everyone? This is just by definition. Okay, so I think you guys have played around with Python enough where you guys are familiar with, like, you know, the whole idea of and versus or. Okay, so the idea here basically is that this is only, C is only going to be true 1 when both of them are 1. Okay, make sense? Okay, otherwise you want the output to be 0. So the way I kind of write this is like, okay, we're going to put in the inputs, which are going to be x1, x2. So that's either going to be 1 or 0, 1 or 0. We're going to define these weights, w1, w2, and b, right? In this case, we tend to write just b as like the bias. It's just like this extra term multiplied by 1. So the idea is if we just adjust whatever b we want it to be, we're going to combine them together and then say if this number is greater than or equal to 0, then we're going to output it to be you know, true or false, okay, which will be either 0 or 1. Does that make sense? Okay, so for example, I'm just going to kind of make something up here. Is that imagine, for example, if this is like, this is 1. Oops, I'm going to draw here. I saw some kind of confused looks. So if this is 1, if this is 1, and let's just set b to 0, so it's nice and easy. Okay, we'd want to put something like, okay, if I put the number 1 here, or let's see, let's say I put the number 0, here, and I put the number 0 here, right? 0 times 1 is 0, right? 0 times 1 over here is 0, so we're going to add those together. Is this number greater than or equal to 0? Yeah, right. 0 is greater than or equal to 0, which means that is true. So the output of putting 0 and 0 in here is 1, which is not correct. In this case, we want, if we put 0 and 0, we actually want the number 0, so false. Does that make sense? So what we're going to do is we're going to adjust W1 and W2 in B to output the correct answer, essentially. Does that make sense? Give me a thumbs up if that sounds good. Thumbs down, you're like, I don't know what's going on. Okay, see some thumbs down. See, I saw a couple sideways. That's perfectly fine to be sideways too. That's just a polite thumbs down, I think. So let's go ahead and check this out. So let's say, for example, I just have 0, 0, 0, right? And so I'm just going to run this a little bit just to kind of show you guys. These are our different inputs. So it's kind of emulating this part, is that if we have 0, 0, we should get false. Okay. If we have 0, 1, like this guy, we should have also false, right? 1 and 0 should also be false. Oops. False. And then 1 and 1 should be true. Does that make sense? So this is kind of like what our inputs are, and these are what the correct outputs should be. Okay, everyone follow me on that? Okay, and this is just by definition of like how AND works, right, logically. Okay, so these are my test inputs and my test, or my correct outputs. Then what we're going to do, we're going to adjust this W1, W2, and this bias B. Okay, and what we're going to do, we're going to feed this into this function that I created up there. And all this is going to do essentially is, if I just wrote this out just mathematically, or, you know, I'll just type it out because that's probably faster anyway. So what this is basically going to look like is saying, okay, this is going to be W1 times whatever input 1 is, okay, plus W2 times input 2, plus the bias term, okay? And then we're going to say, is this greater than or equal to 0? Okay, does that make sense? Okay, so essentially it means that if we have input 0 and 0, we should get this being false because of 0 right here. Okay, or you can think of it like right here, and this should be false. Does that make sense? If we had 1 and 1, we should get true. Okay, all makes sense so far? Okay, so our job now is going to be, how do we adjust this W1, W2 bias to output what we want? So let's just do the simple things like, all right, we're just gonna put all zeros, right? And just see how well that performs. So obviously if this is all zeros all the time, what's always gonna be the linear combination? If I put 0, 0, and 0 here. Or are you gonna give it this equation? What would that combine together? Yeah, it's 0, right? We get 0 times whatever, it's always 0, plus 0 times whatever, always 0, plus 0, it's always going to be 0. Is 0 greater than or equal to 0? Yes. Right. So 0 is always greater than or equal to 0, so we'll always get true, right? So obviously this is not going to work out for every output, but we'll see that at least one of them will work. So if I do this logic now, this kind of function, we see for each input, in this case, the input was 0, 0, the linear combination is 0, okay? Which is 0 greater than or equal to 0? Yes, which is just 1. So was that the correct answer? No, we want it to be 0, okay? And then you can see basically it's going to be the same answer every single time because no matter what we do, we're always going to get 0, right? And it just turns out this last one is correct. Does that make sense? Okay, give me a thumbs up if that's making sense now, if like at least that flow. Sideways? Okay, all right, cool. So what we can do now is like, all right, let's make some adjustments, right? So one adjustment you might try is like, okay, let me just try making bias 1, right? So now always the answer is going to be 1, right? Or I should say the linear combination will always be 1, right? Because 0 times whatever is 0. And then say it's 1 greater than or equal to 0. No, it's always going to be false. So all these activation outputs will be 0, meaning false. And so I run this now. You'll see activations. Oh, I'm sorry, I got that wrong. It should always be true because 1 is greater than or equal to 0. But you can see that linear combination is always 1, right? So obviously this is not very useful, right? It's just going to give us the same output no matter what numbers we put in. We want something interesting, right? So one thing we could do is you can start adjusting like W1, W2. So let's say put like W1 and W2 to be equal to 1. Now what's going to happen is that these are going to be, instead of being just zeroed out, it's going to be 1 times something. So this might actually work out well, right? Is that if we have the input 0, 0, or let's start off with just the inputs 0, 1. Well, input 0 is 1, or sorry, oh my gosh. The first input is 0, which would give us 0 times 1, just 0, right? And then plus W2, which is just 1, times 1, which will give us 1. So 0 plus 1. Then plus the bias, which we just kept at 0. So it'd be 0 plus 1 plus 0. Make sense? Okay. Is 1 greater than or equal to 0? 1 is greater than or equal to 0. So that will give us an output of saying yes of 1, which of course is the incorrect answer. So we'll see that if we've done this guy, this would actually be incorrect. But now you can see here, we are getting different linear combinations, right? We're getting something slightly different. So anyone got a guess of like maybe trying to adjust this a little bit differently? So at least we can get like something a little bit different. We can see we're getting this one correct, but the other two we're not. And note that you can use negative numbers or positive numbers or decimal numbers. It doesn't have to be 1 zeros. You want to take a guess?
Maybe bias -1.
Okay, so you want to keep these as 1 and then we'll put bias as -1?
Sure.
Okay, let's try it, right? So we'll see now is that we'll get a different combination. You can see here, 0, 0. Hey, we got -1, which is correct. We hadn't had that before, right? So awesome. We can see this one's 1 as well. Cool. But these are still not quite, right? So it's like, we still overshot it. In this case, you can see our linear combination was 0, right? So anyone got a guess of like how we can maybe modify a little bit more?
So bias has got to be less than the weighting.
Mm-hmm. Yeah, this bias has got to be.
So if it was -1.5, that should work, right?
That's right. And hey, check that out. So you can see we got all correct. So and the idea here is that we have 1 times 0, and then 1 times 1, and then minus 1.5, which will give us minus 0.05. That is not greater than or equal to 0. So that is a 0 output, which means that is the correct answer, right? Because we actually wanted it to be 0. So that's one way we could definitely have done it. Another way we could have done it too, I have a little solution here, is basically putting each 0.5, 0.5, and then minus 1. But the idea here is the same, is that you want to put something in the bias and in the weights, and then we can actually create this case. You can see it has a different linear combinations, but the output's the same. Okay, does that make sense to everyone? Like how you can kind of adjust this? Now, obviously this is actually not super like, I mean, I don't know about you guys, but this is not fun exactly, like trying to adjust this W1, W2 bias and stuff like that, say what's the right numbers and stuff. But the point is here is that we now created, by you basically making a linear combination and just testing this activation, essentially this linear combination saying, is it greater than or equal to 0? We now created something that can give us functionality. Essentially, it can tell us, is this, it acts like the logical and function here. Okay, so that's kind of like what I'm trying to allude to. And I won't go into like details on this logical OR for you guys going through. We could do the same thing with logical OR, try to adjust these different values and everything like that. And you can see, for example, keeping zeros, it's instead of having this one basically is at least one of them is 1, then C is 1. So you can see all 3 of these are going to be 1, and then the last one is 0 because they're both all 0. So what you could do here is solution, you could put 1, 1, and minus 1, which in that case you can actually see. Again, linear combinations work out, and it does give us the correct output. So again, you can basically create these different functionalities based on just changing the weights and biases. What's nice about these two comparisons is that there's nothing structurally different about what we did here for OR and what we did here with AND. All we changed were the actual weights and the biases. If we just adjust those weights and biases, we can make it do other things, other functionality. Does that make sense? So this is the idea of perceptron. And what we can do now is say, all right, what if we just combine a bunch of perceptrons together and create basically like, you can think of it like a super perceptron, network, which we just call a neural network. Okay, cool. So let's go on and talk about a neural network, right? So we kind of saw a little bit about how those perceptrons can be like used essentially as their own little function going on here. A neural network basically can start creating these more complicated functions. So we've actually you can kind of look at this as that it's very similar to like linear combination, like basically like linear regression. But what we're doing here is a little bit different structure. So this is actually from the curriculum here, is that you can think of like each of these inputs right here, this location, pricing, variety, or variety and offering. Those are kind of like the different features. There's some value, right? Maybe there's some like, for example, location might be, is it in California or somewhere else, or is it, in the zip code, or maybe it's an exact number, or how far you are from, work or something like that. This could be some value here. Pricing, obviously a value, variety and offering. There's some other kind of maybe metric we can use to kind of put this in. You put the inputs in here. And the idea here is that in this neural network, you can see that each of these are perceptrons by themselves. Like if you looked at just this guy by itself, oops. If you looked at just this guy by itself, this is basically a perceptron, right? It's a little kind of like skewed over, but you can see it's taking 3 inputs in here and it's putting 1 output. It's essentially a perceptron. And so you can think of like each of these little perceptrons, which are just called neurons, is kind of like taking in all these different inputs and basically making a decision of saying, kind of like finding these like latent features. So if you remember back when we did embeddings, or not, was it embeddings that we did talk about? Give me a thumbs up if you remember embeddings. Maybe not so much then. If you guys remember recommendation features, recommendation engines or systems, we created like these kind of like with latent features. That's kind of what's going on here. It's like, essentially it's trying to find a way to combine location, pricing, variety of and offering to create kind of like this overall feature of number of people that will walk by. So it's kind of like creating this separate thing by itself. And then it's like, okay, but combining location, pricing, variety, and offering is creating affordability. Remember, we can basically create different functionality by changing those weights and biases, right? So even though it has the same inputs, we can actually define the different weights and biases to give us different latent features, okay? Then with these latent features, we combine these latent features to decide how much it will sell for, or if it will be sold or whatnot. So that's the idea of combining these together into this perceptron. Okay, does that make sense? Okay, cool. I see some nods. All right. Any questions on like kind of like how you can view this as like a bunch of latent features being created? Okay. So you can also think of this a little bit is that we're creating linear separators. So like we saw just above here, like I'm gonna kind of go up here to where I commented something here. We can kind of think of it as like a linear combination together, right, for our perceptron. You can think of these in a lot of ways is that combining each in this part is kind of like a different like linear separator. So if I imagine like taking only two, let's just pretend we only have like two inputs. So just ignore this part right here. There's only two inputs. You can kind of imagine it's like, oh, this is creating a line that looks like this. And this is creating a line that maybe looks like this. And this is creating a line that looks maybe kind of like this. And so the idea here is that you're combining different, of these inputs to create these different, linear separators. So like above and below or left and right and stuff like that. And what's going to happen here, these are going to combine together with, again, these are going to be actually their own separate weights together. And this is going to create, instead of a linear thing, it's going to create something a little more complicated. So we no longer have something that's just essentially a simple line. It's a little more complicated on this. And that's the idea of neural networks, is that we're kind of taking something, the inputs, creating kind of like this overall, feature set, and then getting more and more complicated as we kind of move through it. Okay. Everyone see that? Going from here to kind of a linear separator, and then from here to something a little more complicated. Okay. Cool. So when we can kind of envision this as well is you can see a little bit, in this case, I drew out a little bit of just random data for this point. So you can see like our different data points, and you can say, okay, if I add X plus Y together, is this less than or equal to 0.8? And that will either color, if it is less than 0.8, this is going to give us to yellow. And if it's greater than or equal to 0.8, it'll be colored in purple. So you can kind of see how, even though I didn't draw the linear separator directly, right, you can kind of imagine just having like a simple like line just draw right through here, right, separating these two. Does that make sense? Okay, everyone see that? Like how, like even though I didn't directly define it here, it's kind of like we're just doing here. And what happens now is that we can have multiple layers. So that's where I want you to kind of think about like neural networks is really like creating multiple linear separators and combining them together. Okay, so is everyone following me so far? Okay, I see nods for the most part. Okay, so now we can also think of this as like, if I do this from the curriculum, is you can say like, oh, we're taking in W1, X1, W2, X2, and then we always have this bias term, and we put it together to create this, like this linear combination, right? From that linear combination, like I showed you with the perceptron, we take that linear combination and we pass it into an activation function represented by this sigma. So basically saying, okay, we get some number out of here, and then it's got to transfer that number essentially maybe into a true false, or, true label or false label, or, it's going to be, label 1 or label 2 or label 3. Okay, so the idea is basically transform some numeric value into some value that we actually care about. In this case, usually like a classification. And then we pass that, say, okay, how well did it perform? This is this loss function here. It's saying, okay, how we predicted it to be class 2, but it was actually performed to be class 1, or maybe it was class 2. So the idea here is that we can basically take our prediction here and compare it with our actual value and say, how well did it perform? Okay. And so with that information, what we'll find is that we'll actually use that information to what we call like propagate. We'll do like, how do I say this? We take kind of like this error. This is what this loss function really represents. It's like how bad we did. And we're going to propagate this error backwards and adjust this W1 and W2. So the idea there is that we say, okay, well, you didn't do very well. Let's go ahead and adjust the W1, W2 in the bias terms to say, okay, like we need to adjust this and make it into a better part. And this adjustment actually comes from gradient descent. So it turns out we'll actually kind of like take this error and see how bad it did and propagate it backwards. And we'll know how much to adjust W1, W2, and B with essentially gradient descent. Okay, does that make sense? Okay. The difference is though, this loss function is for one data point, what we'll do in practice is we'll actually feed multiple data points through this network, right? And then say, okay, these are all the different predictions over here. And then we'll have something called the cost function represented with J. I don't actually know why it's represented with J, but it's the cost function. Basically, how well overall it does, like, you know, what M6S is. And we'll take that overall cost and propagate that backwards. So we'll adjust W1, W2, B all at once, essentially, for all the data points. And we keep doing this back and forth. So in general, we'll call this the feed forward, and this will be the back propagation. Okay. All right. Any questions so far? Follow me so far? Cool. All right. So that's kind of the general idea of like how neural networks will be used and how they will train them. So going a little bit into some terminology is the parts of a neural network. We have our layers. So when we talk about, actually, I'm going to show you, where is it? Okay, I'm going to show you this diagram first. I don't know why I have this, I don't have it beforehand. But the idea here is that we have layers. So we have an input layer, basically the initial parameters, whatever we're feeding in the data itself. This will be our input layer down here. So think of like whatever features, you know, we're feeding our network, we're trying to learn from. Then we have our output layer, which is basically saying the classification or the regression. So if we want a single value, if you want to predict the price of the home based on these features, the output would be a single value. If you wanted to output saying, is it a blue home, a green home, a yellow home based on these features that we put in here, this would be, you know, multiple nodes here. So this would be the output layer. In this case, this has just one value, but you could have potentially, you know, multiple values if you have like multiple classes. Okay. And then we have our hidden layers, which essentially these hidden layers kind of hold in like the complex patterns. And so you can see here is our hidden layer, our first hidden layer, our second hidden layer. You could have multiple hidden layers or one hidden layer. You could technically have no hidden layers, but in general, those don't perform in any way. Otherwise, you're basically just doing linear regression at that point. So the idea here is essentially we have these multiple hidden layers that are kind of holding in more complex patterns. Okay. All right, everyone follow me for layers then? Sound good? Okay, so the idea here is that we have multiple neurons that are connected together. It's kind of like you can think of each step going through. Okay, our next part is our weights, which I kind of mentioned a little bit. Basically, you can think of those as like how much we say this neuron matters. So if a larger value exists on this weight, which is kind of represented by this arrow, if you have a larger value, it means that this neuron matters more. Does that make sense? Versus like if you had this, like let's say this weight right here is very, very small, right? Very close to zero. Then it's like, oh, that means it doesn't matter very much. What if we have a really negative value for like another weight? How would you interpret that, you think? Yeah. So if we have like a really large value here, like 10, right? Or this line right here, that means it's really important. You're like, hey, this thing's really important. If you have something that's close to like, you know, really close to zero, let's say 0.001, right? Then this neuron really doesn't affect it very much. But if we had a negative value, let's say this line right here, this weight was like negative, you know, 5 or 10 or 15 or something like that. How would you interpret that? Is it an important neuron?
It's important, and it negates half the effect of the other one. Yeah.
So good. It is an important neuron, right? It's just that it's important in the sense that it is telling you the opposite of like, you know, saying a positive like effect. It's like, oh, like if we know this is here, we know it's going to bring it downward. It's kind of like knowing, like I think I gave this scenario with like movies. It's like if you know your friend really hates the movies you like, right? You know he's actually a great predictor of movies, but basically just choosing the opposite of whatever they choose. Okay, so that's kind of like this, what this negative value would be. All right, cool. So those are different weights. And then there's other hyperparameters, and the next one we're going to talk about is an activation function. So I'm going to show you a little bit of these activations. So remember, is that every one of these neurons basically are just some linear combination of these weights with whatever the inputs are beforehand, and that'll create some number. But then from that number, we have an activation of saying, you know, going between usually 0 and 1. And the idea there is basically we're kind of like adding this extra non-linear decision-making part. And this makes it a little bit different. This makes it different from just making a linear regression, essentially. So it turns out activation functions kind of vary through. But you can imagine every time you see this neuron is that at the end of this, like right before it goes into the next part, there's some activation of saying, you know, what value should be transformed into. Okay. So this is where we talk about activations, like what are those possible parts? All right. So for activation functions, we have a few of them that kind of show, I don't actually know why I have this part run through, but again, the idea of an activation function is that essentially it's adding this extra non-linear part. I'm actually going to skip over that part. I'm not sure why I have this up here first. But the first common one that you'll see is called the sigmoid function, represented with this equation. Don't worry too much about the specific like number, like, you know, or function that's doing. The main thing is to understand like what this looks like and like what the advantages are. So what this advantage here is that basically it's relatively intuitive at classifications. It's commonly used, especially in the past. However, it's not used so much because it's not very efficient in training. It turns out when we propagate that error backwards and back propagation, sigmoid just doesn't do very well in adjusting for the gradient descent. When we have gradient descent, it doesn't tend to be able to be adjusted very easily. So we have something called the vanishing gradient problem, where essentially what happens is that, remember, gradient descent tells us, you know, how we should adjust things to optimize it. Sigmoid, basically, the gradient tends to disappear if it's too small of a value. So it's kind of nice to kind of visualize what this activation is, or what this activation function looks like. So in red here is the actual sigmoid value, or like the function itself. And the idea here is that this X value is kind of like if you start off with, you know, let's say, you know, 5, right, or 5.2, like that's what linear combination gives you. Sigmoid will put out a number that's very close to 1. Note that this value right here gets closer and closer to 1. It never quite reaches 1, right? And if you get something at 0, it's going to give something like 0.5. So the idea there is that there's a less of an activation if the number is close to 0, okay? In the opposite direction, if we go into the negative values, we actually have something less than 0.5. So it's kind of like predicting the opposite. So it'll be a value smaller than 0.5. Okay, does this make sense so far? Okay, so again, remember that what this x-axis represents is essentially, this x-axis represents basically that linear combination where we do like x1 times w1, right, plus x2 times w2. So I can't draw really well, okay? And then all the different features. And this goes all the way together. We basically have our sigmoid represented by the sigma, right? And this is going to give us some value between 1 and 0. Okay. So in the blue here, you can actually see is our derivative. And this is important, is that this derivative is going to tell us how, when we do backpropagation, how much we should adjust our weights, essentially, like how much should we adjust it. The problem is that if we tend to get really high results right here, it's not going to adjust the weight very much, right? If you have very negative weights over here, it's not going to adjust it very much. And it turns out this kind of like cutoff right here, if you look at that, it's not very big, right? You can kind of see is like, if it's over this value, the gradient is relatively small. And you can see even at this 0.5 point, the gradient is about like 0.25, 0.3. It's not super large. The problem is that it turns out, because we'll use backpropagation to adjust our weights, this value right here is not going to do, or sorry, this gradient is not going to adjust our weights very much. It'll be very slight adjustment. Okay, so it turns out that sigmoid functions are practically never used in practice anymore. It used to be a lot, maybe like 10, 15 years ago, but nowadays it's kind of considered like, essentially you'll get slow training and you'll probably never reach the optimal answer. Okay. All right, does that make sense to everyone? Like how sigmoid kind of, this activation function, sigmoid, can kind of take in the value and then output some value between 0 and 1. And like how that represents saying like, oh, it's activated or not activated. Does that make sense? Give me thumbs up, thumbs down. Okay, see mostly sideways. Okay, so this is where maybe I should make things a little clearer. But the idea there is that we have some inputs come in, right, with the weights. We get some value, right? And the idea there is we say, when we get some number, what activation functions in general, just not just sigmoid, just activation in general, is say, hey, like, is this number good? Like, it's like, is this a good number or is this a bad number? And that's what the activation actually is looking at, is saying like, oh, should I tell the next neuron, like this next output? So you imagine like all these inputs coming in to this one perceptron, this one neuron. And it's saying, hey, should I go tell the other, you know, the other neurons that this is a good number? Or should I say, oh, ignore this, like it wasn't, like none of these features actually activate this function. You can kind of think of this as being like, if we went back to our kind of like housing scenario with like latent features, you might say, you know, like this might be like, did the number of people walk by? Like saying, hey, like, did a lot of people walk by or did not a lot of people walk by? And it's kind of saying, okay, well, based on these features, it probably doesn't have that many people walking by. So we shouldn't pass that information to the next layer. Okay. So that's kind of like what this activation looks. It's kind of like the gatekeeper of saying, you know, like, oh, you know, let it through kind of versus like, oh, hold up. Okay. All right. So that's our sigmoid. And so a sigmoid, you know, basically it's like if you have a positive number, it activates pretty highly. If you have a negative number, it activates basically at 0. So it just has no activation essentially. And then in between, you know, it's like, oh, 0.5 essentially. It's like it might have somewhat, it's kind of like a dimly lit bulb. However, the issues is that the gradient, which is the thing that we're going to use to adjust our weights to say, like, hey, you didn't do very well, let's adjust your weight. It tends not to do a great job in conveying that information of saying how much you should adjust it by, which slows down training a lot. Okay, so an improvement to this is the hyperbolic tangent. So kind of just showing you what this visually looks like. You can see really quickly, it looks very similar to the sigmoid. So you can see in the red here. So ignore the x-axis or the y-axis, but you can see it looks very similar in that way, except that the hyperbolic tangent, tan h, is having a lot steeper curve right here. Also goes from -1 to 1, but that's not a big issue. The main idea here is that, hey, like this is a lot steeper, and because it's so much steeper, this tends to actually have a lot more faster convergence. So it turns out that it tends to train a lot quicker. Essentially, it knows if you have a, what's it called? It's going to adjust the weights a lot quicker and a lot more. Versus sigmoid, you can kind of imagine being like, it's a little too careful with how much it should adjust. So that's represented by this steeper gradient, essentially. Some disadvantage to this is that it still suffers from the vanishing gradient problem, because if you have something that's really high, like 10, right, you'd want to really ramp that up. But if you notice like 10 versus like, you know, 5.0, like that's going to be very close to 1. It might be like 0.999. And then like 0.75 is like, oh, that's like 0.9999. And it's like, well, that's barely any difference. So you're not going to have a very quick training overall. Basically, that gradient is going to kind of disappear because it's so small. It's near 0. Okay. So whenever you think of the gradient in this case, and for activation, think of it as saying how much the activation function is going to tell it to adjust the weight. So if you have a very small gradient close to 0, it's not going to adjust the weight very much. Okay. So far, so good. So, okay, hopefully it's kind of coming together. So it's like, okay, like how do we improve this? So this is where we have a ReLU called rectified linear unit. ReLU tends to be kind of the standard nowadays. And the function to look at this is actually really simple. It's basically saying, hey, if the number is positive, just give back that number. So if the number is 10, give back the number 10. If it's 1, give back the number 1. If it's negative, just basically make it 0. So if it's -10, 0. If it's -500, 0. If it's negative 0.001, 0. So the idea there is basically is you flatten out when those negative parts. So what this looks like is actually looks really good, is that in this red right here, essentially it's just like, oh, it's a simple line, right? If the value is 5, just return the value 5. If the value is 10, return the value 10, okay? And you can see here on the negative side, it's like if it's negative, just return the value 0, okay? So some advantages of this is that it's actually really easy to implement. It's actually computationally, it's really efficient. So what actually ends up happening then is that it's actually a very quick way to train. So instead of having to try to calculate those numbers and then calculate the gradient's actually very easy to calculate. Essentially, it's just like, oh, whatever the slope of this line is, right? If it's positive, and then if it's not positive, right, the slope is 0. So it's actually very quick Turns out a lot of libraries actually have this optimization built in. So it's like really good. Some disadvantages. Anyone got to guess like what might be a disadvantage of this ReLU in red?
There's no difference with the negative values impact. So if
Yeah,
it's
basically,
negative 500 or negative 1.
yeah, it can actually slow down a whole lot. Basically, the negative values here, it doesn't know what a worst negative is. It's like, if it's negative, it's bad, but then doesn't know if it's worse. So the problem is that you might not be adjusting the weights very much. In practice, this is usually like not too big of an issue, but it can cause issues as you try to train more and more and more. So there's some improvements you can do. One simple improvement that you'll see quite frequently is a leaky ReLU. So I'm just going to skip over to the visualizations because it's a little bit easier for us to see. It looks just like a ReLU. However, there's a little bit of like leakiness. Essentially, is that you kind of have this very slight negative slope right here. So the idea is that basically if it's more negative, it still will train it. It won't train it like as much as the positive part, but it will still keep it from just approaching zero. So this kind of prevents the vanishing gradient problem. There's other modifications you can have with ReLU. For example, you can have something called like an exponential ReLU. And the idea there is that you might have more of a decay. There's other kind of like variations in it, but in general is ReLU in general is usually kind of seen as the default nowadays. And then if you want to see if you can speed up things, you can check out leaky ReLU. So it can, again, help with speeding training because basically that more negative value is going to be adjusted. A disadvantage of this is that it's not as simple as the, as the ReLU. Essentially, you have to compute some part in the X direction. So in this case, you have to figure out this slope right here. So there is some extra computation, but that might be worth trading that extra computation to more accuracy and everything like that. Okay. Cool. How's this sound so far? Thumbs up if overall kind of get the idea of activations and stuff like this. And you can see there's just different ways to activate functions, stuff like this. And this is a continued area of research of saying, you know, like what are better activation functions and improving the training. And when I say training, you should really think of saying, how do we adjust the weights? And the way we know to adjust those weights is based off of these gradients. Okay, cool. So I see we have a little bit more time. So I just think I have enough time to kind of mention about a few other things. So we're talking about the different parts of the network, right? The layers, the weights, the activation functions. The last part is our other hyperparameters. So these are things that we'll talk more into detail on Thursday, are things like the learning rate, the number of epochs, the batch size. These are kind of the things that we use to kind of optimize our neural network. And remember, a hyperparameter are parameters that are used to, are adjusted to enhance the learning, right? It's not directly saying what the network should do. It's saying how should the network train and learn from the data that we give it. So just note that that's the difference between a hyperparameter versus a regular parameter. But one, for example, like is our learning rate, our alpha. And that basically is like when we're doing gradient descent, which is part of backpropagation, it'll actually be saying how big of a step should we take. So if we're taking a huge step forward or a little step forward, number of epochs or epochs, depending. I actually think in the US, usually people say epochs, but I've always learned as epochs, so I just say epochs, is how many times you repeat this process. So you remember back when I was showing the network, we do a feed forward, we feed all the data through there, and we say, okay, where did you make mistakes? And then we propagate that error backwards to say, okay, we made this mistake, let's adjust the weights and biases so we do better next time. And then we run it again, and then we backpropagate that new error and run it again, backpropagate that error, right? Or backpropagate that error and go through. Every time you feed it forward and then backpropagate, that right there is just going to be a single epoch and everything like that. Okay, so that's what we mean by number of epochs or epochs. Batch size, instead of feeding the whole data set, you can feed in maybe parts of the data set. Okay. And yeah, so those are some basic hyperparameters we'll talk more about in optimizing our neural network. So I kind of want to see if I got a little bit. We mentioned about training a neural network. So this is basically the backpropagation part. So instead of me going through the full process of this, to be quite honest, I think that someone has already done a really great job of doing this. So I think I talked about this channel before, 3 Blue 1 Brown. Does a great job like showing the linear algebra. He actually has a whole like, you know, set of like 4 videos. It's about an hour in total, but I think they're totally worth watching it. So I'm actually going to give it to you guys as like kind of like homework. Is that like watch this, you know, set of videos. It's only about an hour. I think it's something you can kind of just like chill out a little bit and try to watch it through. You don't have to worry about the math. He doesn't try to get too hard into like the derivatives or anything like that. Of like basically how these neural networks work. And I think he visually shows like really well like why neural networks work the way they do. And he does great animations. So I'm actually going to send this out in a second, but here's the playlist. Let's see here. Actually, we don't need the index 4 because that's the 4th one. So I'm just making sure I send you guys the right link. Okay. Oh, that's like an ad. I don't know what this is. Wait. I want to make sure I don't send you guys the wrong one. That'd be funny. All right. So this is this playlist. Again, there's 4 different videos going through a total of an hour. I'm going to send it to you guys through the Zoom chat right now since you guys are all here. And I figure I'm showing this over right now in, what's it called? In the recording. That way, if anyone else wants to look at that, they can look at this specific one. If you probably search for 3 Blue 1 Brown neural networks, you'll find it too. So anyway, he does a great job of kind of visually showing you how neural networks work and how basically backpropagation is kind of done. Okay. Cool. So let's see here. Oh, going back to here. So anyway, I won't go into basically the idea there is that essentially he describes it as kind of like tuning different dials. And I think that's a really great example. It's like, how do you tune the different, you know, weights in the biases to give you the result you want? Okay. And of course, there's some calculus in there, which actually the curriculum does a whole lot through. So I'm not going to focus on that either. Note that if you feel really intimidated by the calculus, it's not needed necessarily in the sense to like understand how neural networks work or even like use neural networks. But it will help you overall to understand. If you understand the mathematics, it'll help you understand like how this backpropagation is actually working and stuff like this. In reality, you're probably never going to have to actually implement it yourself because to be quite honest, usually libraries have a lot more efficient way of doing it than what you could program yourself. So in general, you're not going to write the math, but it's sometimes helpful to understand the idea of gradient descent and how this kind of propagates through the whole neural network. Okay. All right. So before I go though, well, okay, let me ask you guys real quick. I can take like an extra like 5 minutes to kind of talk about neural networks and like how they look like and combine, or I can just wait for it for next time on Thursday. Do you guys have a vote for what you guys, give me a thumbs up if you're like, yes, go ahead and spend the extra like 5 minutes to kind of just quickly look at something. Give me, I don't know, a thumbs down, I guess, if you're like, save it for next time. See like half and I see some half and half. Okay, so I see half and half. I'm gonna save it for next time just because it's not, we will go over it again. And I am kind of over. I'm going to send you guys the link though, so people give a thumbs up. You can definitely play around with this. It's Playground Tensor Flow, and I'm just going to quickly show you what that looks like. Essentially, you can create now your neural network, and you can see these are all linear separators and how these can combine together to make more and more complicated structures. And the idea here, if I go ahead and pause it, you can see like how these are different, more complicated structures. So play around with it if you're kind of curious. Otherwise, we'll talk about it next time. Okay. Cool. All right, so I'll go ahead and stop recording here and